Alright, in this video we're going to look at something called constructing corresponding graphs. Let me start by first explaining what that means. So let's say that we had an object that was accelerating. So I could show that on a distance time graph, and acceleration would be a nice perfect parabola. But I could also show that the object was accelerating by drawing a velocity time graph with a diagonal line that says the same thing. And I could also draw an object that is accelerating on an acceleration time graph and showing that its acceleration is constant. So each of these graphs is technically equal to each other, and they say the same thing, that you have an object that is accelerating. So these would be called corresponding graphs. So in this case, this assignment, we have a velocity time graph that's a little bit fancier, meaning my object is doing more than just accelerating. And I want to know what the corresponding distance time and velocity, or distance time and acceleration time graph look like. So I have to figure out how to draw the corresponding graphs. So it's easiest to do that by making a data table to start with. So that's what we're going to do here. So the first thing I see on my velocity time graph is that this object is moving for 10 seconds. So I'm going to fill in those times in the first data table and in the second data table. Okay, so let's start with distance first. So when I look at a velocity time graph, how do I find the distance traveled? So after 1 second, the object, after 0 seconds, the object has not moved yet. But after 1 second, how far has the object traveled? And you might remember that on a velocity time graph, distance is area under the curve up to 1 second. So that's going to be 1/2 the base times, and it looks like the height is about 3. So that is going to be 1.5 meters. After 2 seconds, the area under the curve is going to be 1/2 the base times the height. Looks like it goes up to 6 now, and that's going to be 6 meters. After 3 seconds, we have gone up like this, and so that'd be 1/2 3 times, looks like maybe a 9, so what, 13.5? And I keep doing this all the way across. All right, when I get to 4 seconds, 1/2 4 times 12, 48 divided by 2 is 24. So I'm going to make myself a little notation here that up to 4 seconds that this big triangle is 24 meters. Because when I get to the 5th second now, you can see that I have to add on this rectangle. And this rectangle is going to be length times width, so that's going to be like 1 up to 12, so that's going to be a 12. So up to the 5th second, it's going to be 24 plus 12, which would be 36. When I get to the 6th second, I'm going to have to add on this little, I'll say rectangle, plus this triangle. When I get to the 7th second, I'll have to add on this rectangle plus this triangle, and then I'll be adding on another rectangle, maybe a little square plus a triangle. So I'm going to take a second and I'm going to find the area of all of those shapes. Alright, so I got an 8, and a 2, and a 2, and a 4, and a 4, and a 2, and a 1, and a 1. So for that reason then, I can write in the rest of my values very quickly. So I have a 46, a 52, 56, a 59, and then a 60. Alright, so I'm ready to graph these. So first of all, I notice that they're all positive distances, and I also notice, because everything that's happening here on the velocity time graph is happening above the x-axis, that everything is happening in the plus x direction. So for that reason, I'm going to make my graph down here with my x-axis right down here at the bottom, because I don't need to have any negative distances. So I notice that my times go up to 10 and my distances go up to 60, and so I have to scale my axes. So I'm going to do that next. Okay, so I decided to go by 2's on the bottom, actually by 1's and label every other one, go by 5's and label every 10 on the y-axis. All right, so I'm going to kind of talk to myself as I do this so that I can kind of make some sense here. But I do notice that the object is accelerating from 0 to 4. 0 to 4. So I would expect that to look like a parabola when I plot the points. So I'm going to plot my points. So I have 0, 0. And I have 1 and 1.5, so it's going to be barely moving there. 2 and 6, 3 and 13.5, and then 4 and a 24. And so when I look at that, it's like, yeah, that kind of looks like a parabola. So I'm going to make a little segment here, a little dotted line for myself, and I'm going to write down the word acceleration because it's accelerating in that spot. And then I notice that from 4 to 5 seconds, it's going at a constant velocity. So I'm going to plot my 5th point. That's going to be at 36. So that would be about right here. And so from this to this, it's going to be a constant velocity. There'd be like a diagonal on a distance time graph. So I'm going to put another little dashed line. I'm going to write V to stand for constant velocity there. And then from 5 to 7 seconds, I'm decelerating. That should look like a parabola down. So I'm going to plot my 6th and 7th. So this is 46, 45, 46. That'd be about there. And then 52, about right there. And yeah, that kind of looks like it's paraboling down. So I'll put a little dashed line here, and I'll write decel. All right, and then I notice from 7 to 8 seconds, it's constant velocity. So 8 is a 56, and so this is constant velocity. Constant velocity on a distance time graph is like a diagonal, so I'm going to connect those like a nice perfect diagonal. And I'm going to put a V there again to stand for constant velocity. And then it is decelerating from 8 to 10. So let's plot the last few points. So for number 9, it is 59, 59, and then a 60. And so that looks like it's parabolating down, and so I'll call that decel. So what I'm trying to show you is that the intervals say the same thing, but the graph looks very different. So this is the velocity time graph, and this is what the corresponding distance time graph would look like. Now let's try to do the acceleration graph. So to find the acceleration on a velocity time graph, we have to find the slope of the line. And so talking to myself, from 0 to 4 seconds, the acceleration is constant. I can see that. And the slope of that would be 12 divided by 4. It's going to be 3. So it's going to be a positive 3 all the way up to 4 seconds. So when you have these numbers here, these numbers, the time values, are technically like the end points of the interval that we're talking about. And then I see from 4 to 5 seconds it's going at a constant velocity. If it's going at a constant velocity, it's not accelerating. So from 4 to 5, the end point being 5, it is not accelerating. So I'm going to put a 0 there. So up to there it was accelerating, and then it wasn't accelerating. Now it is decelerating from 5 to 7, 7 being the end point. And so the slope of that is going to be 12 minus 4. That's going to be 8 over 2. That would be 4. And it's going to be negative 4 because the slope is negative. So I'm going to do that. And then from 7 to 8, I see constant velocity, which means it's not accelerating. And then the last 2 seconds, it's decelerating with a slope of 4 divided by 2 would be negative 2. Negative 2. All right, so the first thing I notice is that I have some positive values and some negative values. So for that reason, I'm going to make my x-axis in the middle of my graph, not at the bottom like I did last time. So maybe something like this. And then I'll make my y-axis over here. And I'm going to go by, I'll call it 2's again, going by 2, 4, 6, 8, and 10. And I'll call this a positive 2 and a positive 4. And we'll call this negative 2 and negative 4. All right, so this is my velocity time graph. All right, so on this graph, What you cannot do is just plot the endpoints, because then it gets kind of confusing. You have to look at it more like what is happening by section. So what I mean by that is I'm going to be looking at these values and at this graph at the same time. So from 0 to 4 seconds, it was accelerating at 3. 0 to 4, 0 to 4 seconds, it was accelerating at 3. All right, so I got that plotted. And now from 4 to 5, it was a 0. 4 to 5. So from 4 seconds to 5 seconds, I got to make a line on the 0. I'll make it kind of dark so you can see it there. But it's not just one point, 5, 0. It's from 4 to 5, and I get that by looking at this section here. Then from 5 to 7, 5 to 7, right there, it was -4. So starting at 5, going all the way to 7, -4. So I plot that. So I guess what I'm getting at here is the acceleration time graph ends up being like a series of horizontal lines. And then from 7 to 8, it was not accelerating. So from 7 to 8, we're going to make a horizontal line there. And then it was decelerating at -2 from 8 to 10. So -2 to 10, 8 to 10. So we'll do that. So honestly, some people leave their graph just like that. Other people like to kind of show that it's like hooked together. And if you want to kind of hook it together, you can kind of make little dashed lines to kind of hook this. And then we can talk to ourselves and say, oh, the object was accelerating at 3, and then it was not accelerating, so I guess it was going into constant velocity, and then it was decelerating at -4, constant velocity, and then decelerating at -2. And so this distance time graph and this velocity time graph and this acceleration time graph are corresponding graphs. They say the same thing, they depict the same motion, they're just shown a different way. So I want you to, if you're an A-Day student, be prepared to turn in your notes to show that you watched the video and that you took those notes. And then you can test yourself by doing the homework, which is just a different one. So it's a different graph, but you're going to do it the exact same way, and we'll be able to see how well you do in terms of being able to construct those graphs and compare them with somebody else. All right, thanks for watching.